Hi, welcome to our Vector Virtual Software Testing Symposium for 2021. My name is Massimo Bombino. I am Business Development Manager for VectorCast in Italy. And today my speech will be about software testing, human or automatic activities. 6 keys to higher quality software. In the next 20 minutes, we are talking about a fundamental question: if software testing should be a manual, a human, or automatic activities. We will understand the differences not only from a language point of view, but the fundamentals of real software testing versus other form of automated testing or automated analysis. And then finally, we are going to summarize which are the 6 keys, the 6 steps to reach higher quality software. Either you are doing certified safety critical software or other form of mission critical or business critical software. So the first aspect that we are going to discuss is why software is so different. So different from what? Different from, for example, the electromechanical device. I don't know if you are aware of the bathtub curve of the electromechanical devices that could be applied to humans and to babies too. This is the description of the failure rate during the life of a mechanical device or a human. There is an initial burn-in period where you have higher failure rate because the baby is more delicate than adult, and because you have a new device that is on the market. So there could be some defects that are still in the device. Then you correct the initial problems of the burn-in period, and you have the useful life, where the probability of failure, or the MTBF, the reciprocal, is almost constant. And this is the same for a human, because from 6 months of age to about 60-70 years, you have a flat failure rate, flat death probability. And then there is the wear out period, where you have for a mechanical device, a electromechanical device, you have obsolescence. For a human, you are old, so you could more subject to illness and to other problems. And the same for the electromechanical devices that could have some obsolescence. If we talk about software, if we talk about the different components, the early infant mortality failure rate, the burn-in that we just discussed, and the wear out, the obsolescence in yellow that we discussed before. And we talk also about the constant random failures. So these are the failures that could happen at any time. You could not foresee them, you could not avoid them. These are some failures. For example, if we talk about the humans, if you cross the road and you have an accident, or you have another kind of a car accident or your home accident, these are not predictable and it's very hard to avoid them. The final observed failure rate is the famous bathtub curve. But what about the software? The software is something that is subject especially or almost only to systematic quality errors that are in the original project, in the original design, and they were missing by the verification activities, and the failure rate is really unpredictable. So you will have probably a flat, a constant random failure rate like the green line, and you could not remove much of the errors in the infant mortality period. Then as soon as the software is on the market, you can try to remove some problems, but then the constant failures are very, very hard to remove. So in effect, if we talk about electromechanical device, we talk about the product assurance. So you can calculate the failure rate, the MTBF, mean time between failure. You can do some assessment of failure mode, etc. You can give a probabilistic and precise estimation of the probability of failure in time. You can study statistical models, you can do lab tests, you can analyze historical data, etc. And what are the aspects of product assurance? That applies only to simple and finite systems only, where the number of input-output is small, the number of state is small, is reduced. In this way, you could reach integral testability. So you could predict, simulate, and test all the possible input and all the possible output, thanks to truth tables, to lab tests, models, prototyping, etc. And in these cases, you can reach fully automated testing, and you can reach probably also 100% correctness. An example of this kind of things are IKEA chairs. Maybe you have seen in front of IKEA a device to test IKEA chairs with a piston and simulating a person that is sitting down, weighing 80 kilos every day, maybe 10 times a day. And it's applicable also to capacitor, to resistor, simple electromechanical device, simple chips, for example, flip-flops, etc., but not to software. To software, you could apply only process assurance. That is totally another kind of thing, because it's based on a concept of a formal process. So in order to do good software, you need a formal process, formal plans where you describe what you are going to do on your software. You need very good requirements and modeling. You can also model your requirements. You need continuous testing, and you need a process certification if you have a safety critical software. So in this case, you could not give a probabilistic estimation of failure. There is no way to establish the probability of a failure of software. So you could not build for software statistical models, but you can just build a very robust process. The fundamental concept of process assurance is applicable only to very complex and infinite systems, like software, for example, where you have a big number of input and outputs, a big number of internal or external states. So you can reach a partial testability. So you could not test all the possible IOs, but just some of them. So no full automation of testing is possible. And we will talk about what is automation, what is manual, what is automated, because there is a difference between these terms. And process assurance is typical of complex electromechanical systems and of software. So our interest is for software. Because software is something so new in the history of the humankind, because it's one of the most complex intellectual activity. Is any phone that any app that you have on your phone is more complex than the Dante's Divina Commedia or Michelangelo's Cappella Sistina or any other human intellectual masterpiece of the history. In terms of man years. So this kind of complexity, this kind of problems could not be handled with traditional techniques and approaches like engineering, traditional engineering, civil engineering applied to buildings, applied to bridges, etc. And software could not be approachable with statistical and quantitative analysis and similar approaches. Software could be handled only by methodological approaches where the process is the real king. So you should not concentrate on statistics, on tools, on this kind of things, but you should be more aware of the process, more aware of having a robust process. And then the tools will help you to reach this objective. But you should not start vice versa. You should start from the process. So some definitions. If we talk about manual testing, what we are talking about? When you manually write a driver to test your function. For example, if you write a main and then you write manually some code to test your own code. Of course, this approach is very slow, very expensive, because you almost write one line of manual testing code for each line of code, and is quickly disposable. It's quickly out of date, so you could not use it anymore. If we talk about automated or automated testing, what we are talking about? It's not easy, it's not a definition that everybody agrees, okay? Vectorcast, for example, our tool for software testing, allows to create automated test drivers, where you can create, Vectorcast could create for you all the main, all the support files. Everything is automatically created, compiled, and linked into a harness. So this is really automated, okay? And the GUI, the Vectorcast GUI, allows you to create input and expected value for your own function, for example, F1 and F2. But still, the creation of test cases is and must be a manual and human activity based on requirements, as we will see in the next slide. Of course, you could also create automated regression testing. Once you have created the test cases, then you could run an infinite amount of times endlessly, because you have, for example, tools like Jenkins and other frameworks that allows you to do continuous integration. And we will talk also about that. And also another kind of automated activity is the basic path coverage. That is called also test case generation, but is not the correct definition, because this isn't properly testing, because there are no expected value. So the test cases are created just to maximize the coverage, not to test the software. Even if some form of robustness test could be created thanks to this automated basic path coverage. What are the 6 keys to higher quality software? The first is to follow a good software development process. As we discussed about before, there are 2 kinds of software. The business or mission critical, so the regular software where no life is in danger, but the business or the mission is critical. There is no mandatory certification. So there are some quality standards that you can decide to follow. For example, the ISO 9000 standard, but is for some minor and organizational aspects. Or, for example, there is the ASPICE, the automotive SPICE, that is pretty good for having a good process. And, for example, the METS, the method for efficient development of software. And then there is a safety critical software, where the human life is in danger, where you have a mandatory certification. For example, automotive ISO 26262, avionics DO178C, medical IEC 61304, industrial EAC 61508, and railway EAC 5128. The second key is to write perfect requirements. What is a perfect requirement? Safety critical software needs are different than business critical software. So you should have probably a different degree of criticality. But small and medium enterprises are also different than big companies. And small teams is not like working in an international project. Nevertheless, there are some common factors, because there are some properties that are mandatory for everybody, for any kind of company, because the requirements themselves in various forms are mandatory for everybody. So requirements are always needed. Then, of course, the rigor, the completeness, the rules could change, but the requirements are always mandatory. And so you should write very good requirements, perfect requirements. Avoiding requirements using other form of specification, etc. could be a big mistake that you should not do. Nobody could miss the requirements independently of the dimension of the team, the project, of the company. And in order to have a good software, to reach good software quality, you should make the effort to invest your time in a very good requirement analysis and to write very good requirement specification. The third aspect is to adopt, once you have a good requirement, then you unlock the third key to have a good requirement-based testing approach. For example, if we look to this piece of code, you see there are some line of code, this function with x as input, and some code. You don't understand this code, so you if you have to test this code, I don't know, maybe you see there is a for loop, etc. But what about if I tell you the requirement of this piece of code? Okay, I tell you that this is the definition, the requirement of a sin function. So the projection of a vector of radius 1 and angle x on the y-axis. Okay, then it's much easier to understand, because you could add some robustness definition of the requirement. For example, you could tell that the angle is between minus p and plus p, plus minus 2p, and you can tell that the sin of plus or minus infinite is not a number, and the sin of not a number is not a number. So now we have a complete requirement, a complete definition of the sin function. And if you want to test now this function, it's very easy, because you remember of the school, the sin of some angles. The sin of 0 is 0, the sin of p divided by 2 is 1, and so on. The p divided by 4 is square root of 2 divided by 2, etc. So this is a requirement-based unit testing. This is what you need to do before to go with VectorCast. Do you really care about the implementation, about the code? No. This is a way to do real black box testing based on the requirement, so a requirement-based testing approach. And of course, you can use a VectorCast requirement gateway for traceability between your requirements and the test cases. The third key is to perform software testing on all phases of software development. Starting from the implementation, you can do software unit test, so you can perform white box testing on host or on target thanks to VectorCast C++ ADA, and thanks with the RSP, the runtime support package, to run on the target. And then you can do software integration test, where you do software integration testing activities and coverage on your host, on your PC, with Canoe, Vita Studio, Virtual Target if you want to emulate some hardware, and again VectorCast C++ ADA, and you can start to collect coverage with VectorCast QA. And then you can do hardware integration, system validation, and coverage on the real target, on the real ECU, and you can start to do change-based testing, as we will see is our final sixth key. With the Canoe, with the Vita Studio, with the VT system, so you can do hardware in the loop testing, real physical I/O testing, and the VectorCast QA to collect the coverage. Of course, then you can use VectorCast Manage to organize your activities, and Analytics to show metrics and KPI. And the benefits is the full support of the overall software development life cycle, from unit test to system validation, and the other advantage is to uniform the test management, test automation, results analysis, and traceability. The fifth key is to do continuous integration with Jenkins and VectorCast. The objectives are to achieve faster turnaround cycles, to find as many errors as possible, to do parallel and virtualize headless test execution, to identify test cases to be executed because of code changes, because of previous test failures, so rerun the test, change the requirements, new requirements, new safety critical requirements, and so on. So you can use Jenkins as a master, and then VectorCast manage with a different project and the physical nodes where to run the test, or the virtual nodes. And with VectorCast QA, you can collect the coverage, you can create test suites in multiple configuration, you can support massive parallel testing with the continuous integration servers like Jenkins. You can support change-based testing. We'll talk about this in a few minutes. And you can have a Canoe controlled by QA with a com script, and then to show the result in Jenkins. So you can then use a VectorCast using the command line or Python or the Jenkins plugin. And then finally, you can perform change-based testing with your VectorCast. In a normal regression testing, you need to rerun all the test cases, unit integration test, system test cases. And it takes a lot of time. It could take days or weeks, because some hardware tests are very long and the test results are very difficult to analyze, okay? But what about if we collect the coverage with VectorCast QA and we keep the source code traceability? The big advantage is that with the change-based testing, then thanks to the code coverage, providing traceability between the source code and the test cases, VectorCast determines which test cases have been affected and will rerun just a very small subset of the test cases. So in a fraction of time, it could be 1,000 times faster than a full regression testing, because only the test cases that has been changed will be rerun in order to reduce the testing time, to find errors faster, and to improve testing efficiency. So it's now time for your questions and answers. Thank you very much for your attention, and I'm here to answer your curiosity, your questions, and whatever you want to ask. Thanks.